A 10-kilogram box is pulled along a horizontal surface by a force Fp. We can say that that's F pull. Really, we know this is an applied force. By a force Fp of 40 newtons applied at a 30-degree angle above the horizontal. Assume a coefficient of kinetic friction of 0.30. Calculate the acceleration. Now is also a good time to remind you that coefficient of kinetic friction, well, that depends upon what materials are involved here, and it's just a number. The coefficient has no units, so this is correct that it has no units here. It's just 0.30. Now, the first thing you want to do if you're ever trying to approach a situation is to draw a sketch. But that's already kind of happened for us here. So let's say this is our sketch and that we're ready to move on to the next step. Now there is certainly a more official kind of diagram that we can draw, and that of course is a free body diagram. So step 2, to draw a free body diagram. And that just makes it a little easier for us to resolve the forces, which we will have to do. So we can draw the object even as a dot. My pen will let me. That's my beautiful dot there. All right, we have the normal force, of course, because this object is sitting on a surface. We have the force of gravity, which we also know as weight. And we know that both of these things are equivalent to mg, the mass times the gravitational constant g. Now in this case, we have our applied force Fp that's coming up at an angle here. So it is not going right along our x-axis. So here's our angle of 30 degrees. Here is Fp. And then finally we have friction. Friction, of course, will always oppose the direction of motion. So it is safe to assume if we're looking for the acceleration that both the motion and the acceleration are occurring over to the right or to the positive x direction. And we can assume this because friction is pointing to the left or the negative x direction. Now, if I look at this force Fp, it is not aligned with our typical XY axis here. Let's look at our other forces. Normal force and force of gravity or weight, those are both along the y-axis. Perfect. Along the x-axis is friction, but Fp needs to be resolved into components. So we are going to end up with some components, Fpx and Fpy. Now please think to yourself in this moment, what type of math do we need to use when we can draw a wonderful right triangle here? Feel free to draw one prettier than mine in order to determine these components. Well, of course, as I'm drawing this right triangle, you should all know by now that we will be using trigonometry. So I do want to take a moment to remind us here of our problem solving steps. So the first one, anytime you're approaching a problem that seems a little complex, is to draw a diagram. There just happened to be one for us. So here's our sketch. Number 2 is to draw a free body diagram. Now, many of you who are feeling more comfortable might jump directly to the free body diagram. We are now at the point where we've chosen our axes, and it does seem rather convenient to choose those aren't very straight, x and y axes as we typically would on our plane. And next we are going to resolve our vectors. So since we expect our motion to be horizontal here, we've chosen our axes in the x and y, and now we will resolve this vector that does not match along our x and y axes. So we can start with the component of Fp in the x direction. Well, that's going to be Fp times, so this is the magnitude of Fp given to us in the problem, Fp times cosine of theta. Theta is also given to us in the problem. So let's start with this one. We can plug in numbers. The magnitude of this applied force FP is 40 newtons. So we can fill in 40 newtons right here. All right, times cosine of theta. What is our theta? 30 degrees, a 30-degree angle. So times cosine 30 degrees. If you plug all of this into your calculator, you should get something along the lines of 34.6 newtons. And that is our x component of this applied force, which is applied at our 30-degree angle. Similarly, we can find the component in the y direction. Still using trigonometry, the component of this force in the y direction is Fp times sine of theta. Once again, let's plug in our numbers. Fp is still 40 newtons as given to us in the problem, times sine, and theta is still 30 degrees as given to us in the problem. We can now plug all of this into your calculator and you should get something along the lines of 20 newtons. So what we now have are, rather than this inconvenient force applied at an angle, these nice convenient forces of 34.6 in the x or horizontal direction and 20 newtons in the y or vertical direction, which are much nicer for us to work with. Now here's something that I always like to do at this stage in the problem. We've just resolved this force into its components. Let's draw, or rather redraw, our free body diagram. So here's our little free body here. It's what we call the dot or the box that you draw in the middle. Well, that nice normal force, that was still in the y direction. Our gravitational force over here, also known as the weight, also known as mg, so I'll just write mg since we may be using that, is right here in the y direction. Our friction is still opposing our motion, and that is in the x direction. And then we had these lovely components that we came up with. So our component in the x direction of our applied force, which we kind of wrote to be Fpx, well, we calculated that, and that turned out to be 34.6. We also calculated a component in the y direction, and this is going to get a little messy, but sometimes I draw that just by drawing it right on top to show that these two would add together in the positive y direction. We calculated that Fpy, meaning the y component of the Fp applied force, well, we got 20.0 newtons. So now we've redrawn this to all conveniently be on an XY plane. And I swear every time I draw an XY plane, it's a little bit worse than the last time. But our math is now going to be a lot easier, and we have been asked to find the acceleration. So at this point, you should be asking yourself, what direction will we apply Newton's second law? If we're looking for acceleration in a problem like this, pretty safe to say we are going to be using F equals ma, or Newton's second law. Well, earlier we determined that this acceleration is being pulled along the horizontal surface. So the acceleration is going to be in the positive x direction. That means we want to use this form of the equation. The sum of the forces in the x direction equals mass times the acceleration in the x direction. Mass, of course, is a scalar, so it does not have a direction associated with it. Now, here's the part that tends to be a little bit tricky for some of us, is moving from this form of the equation to one that includes all of our other forces. What we do is we replace the sum of the forces in the x direction symbol here with the actual sum of the forces in the x direction. We need to sum those up. Now, this one, this x component of the applied force, that's a positive x direction force. This one, the friction, that is a negative x direction force. So when I sum these up, I'm going to account for that. So I'll replace this part here, this sigma f in the x direction, with the component in the x direction of that applied force. This is positive minus that friction force that we determined to be negative. And then all of this, of course, will be equal to MA, where A is in the x direction. So you can really do this next part of the problem in a different order. So keep that in mind, but here's the order I'm going to do. I know I'm eventually looking for acceleration, so I want to set that up symbolically in the simplest form possible. If I rearrange this whole thing through algebra to isolate the acceleration, then I'll end up with Fpx minus friction force all over m, the mass. Well, Fpx, we've calculated that. The mass, that's given to us. So what's the only other thing we need to solve for in order to find the acceleration? Now we know, of course, that there are two different kinds of friction. There's kinetic friction and there's static friction. There is an acceleration here. That means the object is moving. So we're looking at kinetic friction. Well, what's our kinetic friction equation? You should have this in your notes from long, long ago. The force of friction for kinetic friction is equal to the coefficient of kinetic friction. This is known as mu k, the coefficient of kinetic friction times the normal force. Well, now we have to think, what is the normal force? We've done a lot of practice on calculating the normal force. In this case, just as a brief review, and then I'll give us the number because our focus is on friction today. In this case, our normal force has this additional component also added in the same direction, and then mg. So if we did m times g, that would be our 9.8 times 10, which would give us 98 for the normal force to balance out. But since we have this extra pull up in the y direction, we know from apparent weight problems that the normal force has less work to do to balance out the weight. So the normal force is actually going to be less than the weight in this case. Please go back and review some of the contents from normal force and weight that we practiced last week. I'm just going to go ahead and plug in some numbers so we can get moving with this problem. But if you don't know how we would calculate the normal force in a case like this, let me know, and I'm happy to point you to the relevant resource. We are looking for the force of kinetic friction. We have mu k, or the coefficient of kinetic friction, 0.30, no units as it is a coefficient. And the normal force in this case, if we go through all of our lovely steps to find the normal force, would be 78 newtons, or something very close to 78 newtons. Once again, if you don't know how we would calculate this, I suggest you look back at normal force and weight problems. If we multiply these two together, we get a nice numerical value for the friction force of 23.4 newtons. And that was our last missing piece of the puzzle here. So we can plug in some numbers and finally solve for our acceleration. We had our component in the x direction we found very early in the problem, probably feels like a long time ago, was 34.6 newtons, minus the force of friction that we just calculated, 23.4 newtons, all of this divided by the mass of 10 kilograms. Now feel free to check this in your calculator. We are now just plugging in numbers, and we should find something around 1.1 meters per second squared. What this is telling us is that this box, with this applied force being pulled up at this angle here, gives us 1.1 meters per second squared acceleration in the positive x direction.